I welcome you all. Today we will see how to solve transmission line problems using Smith chart. So before going to the problem, let us see what are the basic characteristics of Smith chart. So Smith chart is generally used to detect transmission line characteristics such as input impedance, reflection coefficient, standing wave ratio. So instead of going for a tedious uh, equations solving, so we are going for finding the same characteristics using Smith chart. So if you see this Smith chart, we can find many circles, right? So one such circle is called resistance circle. So whatever circle which is centered around this part is called constant resistance circles. Okay. So these are the circles which have constant resistance, constant radius. Then coming to that reactance part, so the what the circles uh, which tending outward, okay, these are the reactance circles. So you can see some of the reactance circle tending towards in this side, and few more reactance circle which is tending leaving out from this side, right? So from this you can say this is a constant resistant line, so it can be used to find the standing wave ratio. Then you can say it's a resistance value. Similarly, we have a reactance circle. So upper part you have inductance reactance, so you can say R plus jx, and lower part it is a capacitive reactance which is R minus jx. So whenever you are getting the value of impedance, according to the we need to plot. So the center line shows the normalized impedance value, real part resistance, or similarly the outer line shows the reactance value, where the upper part of the Smith chart shows inductive reactance, okay, the imaginary part, whereas if it is minus, you can say it is a capacitive reactance. This value can be plotted, represented in this below circle. So we got this resistance line, reactance line. Apart from that, the standing wave ratio can be obtained. You need to, so after plotting that, mapping the inductive or capacitive reactance, whatever the value given, then from that you need to draw a circle. From that we will find the standing wave ratio. We will find the reflection coefficient, angle of reflection coefficient. Okay. Then if you are seeing the circle, right, the full circle is meant to be lambda by 2. Okay. The full circle is meant to be lambda by 2. So you know that one full circle consists of 360-degree angles. So we can say one lambda which is 720 degree. Okay. So for one full wavelength to cover, we need to rotate this twice. Okay, it has to cover twice of this Smith chart. Then this should be toward. Apart from this, we have few other parameters. So we have seen resistance circle, reactance circle, what is standing wave ratio, what is lambda, right? So apart from that, towards generator. So based on the problem, we need to find that angle. So outer part will help you to find that what is the lambda value, angle. Okay. So you can say it's a clockwise. Okay. So clockwise, you can say it's a toward generator. And anti-clockwise, you can say if any movement is from anti-clockwise, it is toward load. So based on the question, we need to identify, and accordingly we need to move. Okay. So we will start with one problem. So let me read the question. So they asked a lossless transmission line with the characteristic impedance of Z0 50 ohm is 30 meter long and operates at 2 megahertz. The line is terminated with a load is at a load impedance 60 plus J40 ohm. If velocity of light v, velocity of propagation v, is 0.6 times the velocity of light on the line, find the following parameters. On the line, find the reflection coefficient, the standing wave ratio, and the input impedance. So we are going to use Smith chart to find this problem. So this we are using instead of going for some complex calculations involved. So using the Smith chart, it's easily you can find. So you can avoid using the softwares also to find the transmission line related problems. So we will start with the problem. So first they asked to find reflection coefficient tau. So to find the reflection coefficient tau, we need to plot that given normalized load impedance, right? So we need to find the normalized load impedance. So first we have to find reflection coefficient tau. Okay, so we want to go with the normalized impedance ZL dash. So ZL dash, so which is given by load impedance divided by characteristic impedance. Okay, so where load impedance is given as in the question 60 plus J40 and characteristic impedance is given as 50 ohm. So by simplifying this, we are getting 1.2 plus J0.8. So now as I told already, so we have found the normalized load impedance, which is ratio of load impedance and characteristic impedance. So we got 1.2 plus J0.8. So now we come to know that it's a impedance reactance because it's a plus. If it is minus, it is a capacitive reactance. So now we need to plot this. So as I said, it's in the form of R plus Jx. Since R is a constant resistance, so we need to find where the 1.2 is there. So in the center line, if you see, it is from starting from 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4. So where we need to see 1.2. So this is 1.2 is there. So just mark a point over here. Then it is 0.8. Okay. So 0.8 is a reactance complex part. Since it's a plus, that is inductive reactance, we need to see the upper part. So see the upper part where it is 0.8. So if you see a 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So I have marked the 0.8, 0.8. So now, so both this 1.2 resistance circle and this 0.8 inductive circle, where it meets, that point you should note down. Okay. So this 1.2, it is going here and this point it we are getting here. So it meets here. So both this circle meets point here. So let us take this is ZO and this point is P. Okay. So OP, what you have to do? So first you have to find the reflection coefficient, right? So using the scale, we need to we need to draw a straight line from O. It's still extending the outside, our full circle. Okay. So from O is where point is 1.0 resistance value. Okay. So from O, P, I need to draw a straight line. So from here O, so using the scale, please draw it. So from OP, leaving towards outer circle, we need to write it, right? So where it meets this point at the outer circle, we need to take it as a Q. So immediately where it meets here, it is Q. Okay. So our aim is to find deflection coefficient, right? So how to find deflection coefficient? So reflection coefficient can be found. There are in few Smith chart they given the bottom they given reflection coefficient. We can also use that. Okay, here we can also use to find that is magnitude. So reflection coefficient consists of both magnitude and angle. So it can be found by taking the ratio of OP by OQ. So what you have to do? Take a scale, measure OP and measure OQ. Take the ratio, that is magnitude of reflection coefficient. So OP is approximately coming around 3.2 centimeter, whereas OQ is coming approximately 9.1 centimeter. So by taking this ratio, I'm getting 0.3516. So we have found that magnitude of reflection coefficient, but we want to find angle of reflection coefficient, right? Because it consists of tau and theta of tau, right? So we need to find both magnitude and tau. So how to find the angle of reflection coefficient theta tau? So this is where the angle between this line from origin line to its OQ, OP. Okay, this OP line, the angle between origin point towards OP, that is your angle. Okay. So if you see this point, its angle is given, say 0, 10, 20, 30, 40, 50, 60. So it is between 50 and 60. So it is if you are accurately, it will be some 56 degree. So now you got the value of reflection coefficient, which is magnitude 0.3516 and angle 56 degree. Sorry, 56 degree. So now we have found the first initial part. Let us go with the second part. So second is standing wave ratio. So standing wave ratio is not that much difficult, it's easy. So you need to take a radius OP and okay, OP, this point, right? From this you need to draw a circle. You have to use compass. Okay, don't write in freehand. So please take compass. So we need to draw a circle. So from OP, so we need to draw a circle. So draw a circle making the radius OP. So now where it cuts at the resistance circle, we can say it is the standing wave ratio. Okay, this point You can say it's standing wave ratio. So standing wave ratio is, if you see, it's a 1.2, 1.4, 1.6, 1.82. It is slightly above 2. So I can say it is 2.1. Okay, it's coming 2.1. It's around, if it is plus or minus some value, it's not an issue. So standing wave ratio is 2.1. So third, they asked the input impedance. So we need to find the input impedance. So input impedance, they are given certain uh, at the particular length of transmission line, we need to find it. Okay, so for that we need to have the lambda value first. Then we will find what is the length of that transmission line in terms of wavelength. According to that, we need to see that. So first, let us find the lambda, which is wavelength. We know that it's a lambda is a velocity of propagation by f, where the velocity of propagation of the transmission line is given as 0.6 times the velocity of light divided by f. We know that 0.6 and velocity of light is 3 to 10 power 8, and frequency is where its operating frequency is given 2 megahertz, which is 2 into 10 power 6. By solving this, I am getting the lambda is 90 meter. So lambda is 90 meter here. And we want to find the length. They given the length as 30 meter, but we want in terms of lambda, because you know that it is related with the lambda, right? So how to find length in terms of lambda? So 30, so I want in terms of lambda. So the corresponding lambda value, you got it from the given value, it's 90 meter. So for example, it's similar to converting radian, right, pi to angle. So if you want to, from the angle you want to get the pi value, so you will be multiply pi by 180 degree, right? Or else if you want angle 180 by pi, you will do that, right? So in similar way, so 30 meter long is given in terms of lambda, so I want to get it. So lambda by 90, I will give in terms of lambda. So we know that 30 by 90, 1 by 3. So lambda by 3. You know that lambda, previously we have shown that, okay, lambda by 2 is 360 degree. One full circle is 360 degree. The lambda is 720 degree. So lambda is 1 by 3. So lambda is 720 degree divided by 3. So I am getting 240 degree. So there is a angular movement in order of 240 degree towards the generator or away from the load in the clockwise direction. So at that point, the input impedance will be placed. So we need to find the place where towards the generator it should have a 240 degree. So from the point OP, OQ is there, right? So as I told, it's a toward generator, right? So toward generator clockwise, we need to find, or else we are also saying it's away from the load. Then that's what it comes under clockwise direction. So from this point OP, OQ, I need to rotate 240 degree. So at that place only my input impedance is there, because length, so we have found length of the, sorry, we are finding input impedance, right? So the input impedance can be found by making, rotating 240 degree from the point you achieved. So from here we need to rotate to 240 degree. So there is some simple tricks. So the overall angle I said is 360 degree, right? So one full circle. So half of the circle you can say it's a 180 degree, right? Fine. So already from this origin we have found the angle, right? From the origin it is 56 degree. So this angle is 56 degree. So theta L, theta tau. Now they want to rotate 240 degree from here, right? So please see that from two already 56 degree you are covered from here. So how much else you need to cover? So just to do 240 minus 56. Okay. So 240 minus 56. You are getting 184 degree. Okay. So this covered by 56 degree. From this origin point, I need to cover additional 184 degree. I said that one half cycle is 180 degree. So it is rotating from here to here 56 degree, right? Then from here to here it is rotating. So it is 180. It's covered 180 degree, but to for the corresponding length it's 184 degree. So from here I need to go with the additional 4 degree. So 180 is, so 1, 2, 3, 4 degree. This 4 degree. So this point. So what you have to do, from the center point of 1.0 you need to draw a line. Okay, at this point. So now we want to find the input impedance. Okay, so we know that input impedance is a point where this circle meets that point you need to take down. Okay, so if you see this point is met, right? So you need to find the corresponding resistance value here. Okay, what is a corresponding resistance value here? That resistance value should write, and corresponding this outer reactance circle where it meets. So this one where it meets. So this reactance is XL. So that we need to find. So it is coming, if you see, it's coming, it's not exactly drawn. So if you drawn around, it's coming here. Actually, I didn't draw with the proper compass, right? So if you draw the corresponding circle, it's coming R is around 0.47, and this angle is, this reactance part is coming. So this is 0, this is 0.1, right? So then it is around some 0.03, 0.04 only. So this line, it's 0.1, 0.2, so it's coming very less. So it's a 0.03. Okay, so we got Z in. Okay, Z in value as resistance, which is 0.47, where it cuts the circle, this point, and the reactance part at this point is 0.3. Since it is above the upper half of the circle, it's a inductive reactance. If it is below the resistance line, you can say it is a capacitive reactance, then it should minus should come. So in this case, it is not a problem. Then one more thing you should remember, this is normalized input impedance. So if you want input impedance, the value should be multiplied with the characteristic impedance 50 ohm. So by multiplying this with the 50 ohm, so you'll be getting the exact input impedance 23.5 plus J 1.5 ohm. So simple. From the given normalized impedance, take a ratio and apply that value. So resistance circle and reactance circle, mark a point P, then OP, OQ you need to find. So by taking the ratio, I'm getting the reflection coefficient magnitude, where it cuts at this angle from origin. OP angle is a angle of the reflection coefficient. And standing view ratio, we need to draw a circle with radius of OP. After drawing the circle where it cuts the resistance line, it is standing view ratio. Third one, you need to find the input impedance. We need to find the lambda. So given is 0.6 times the velocity of light or the frequency f. So you got 90 meter. So I want L in terms of lambda. So they given 30 meter long. So 30 into lambda by 90 will give you 240 degree. So I need to move around 240 degree from this point. So I have to move around almost in this point till it reaches here. Then from here where it cuts this circle, from here I need to find this point as well as the right hand circle. This point is 0.47 plus j 0.03. Since it is a normalized value, we want to find the original input impedance. So multiply with the Z0. So I'm getting corresponding value. So apart from that, we can find many parameters and we can go for single stub matching, double stub matching. Thank you.